I'm opening the YouTube. It's almost there. Okay. Now we are live. All right, I'm going to share my screen. And like I said, we're going to work on it because I was just creating the PowerPoint. And this is a small presentation for you. Slideshow from, oh, I don't think it's going to be a slideshow. Well, let's go ahead and start with the presentation, and let's get into, just going to talk about shunts today, right? The basic of the shunts is we're going to have three types of cardiac outputs. We're going to have to get the difference. The cardiac output that we know that we've been practicing before, and as we have established, is the volume of blood pumped by the heart per minute. Basic, right? We're talking about just a regular study. There's nothing else to suspect. Regular cardiac output that we do every single day in the cath lab with the right heart, right? Now, then we have a shunt. When we have a shunt, we want to know the difference between the systemic cardiac output, which is the blood that goes between the aorta and the right atrium, right? So when the blood leaves the heart through the aorta until the blood comes to the right atrium on the other side of the body. Yes, so that will be your systemic cardiac output. Yes, and then we have pulmonary cardiac output. That will be the blood volume pump between the PA and the PV. That means is the blood that goes to the lungs. Now, remember that when we talked last week about, for example, the impella, the amount of blood that the right ventricle pumps to the lungs should be the same amount of blood that the left ventricle pumps out to the system. So it should be equal. In a healthy person, or let's say not in a healthy person, but a person without a shunt, the systemic cardiac output, which is the blood that goes through the body, should be the same blood that is processed through the lungs. Does that make sense? We get what we put in. Yes, even though the right system is a low pressure system, it does pump the same amount of blood to the lungs, and then the left heart receives it and sends it out to the body. So the ratio should be 1:1. So it should equal. The systemic cardiac output should be the same as the pulmonary cardiac output. When it's not like that, that's when we have a shunt, or we can suspect of a shunt. Okay, so let me go on to the next slide here. So here I kind of gave you, we're going to use the cardiac output formula and dissect the cardiac output formula, or apply it to individual cardiac outputs, the systemic, which is QS, and the QP for the pulmonary system. Remember, Q, it's flow. Okay, so let's go on to, let me get my annotation tools, because I really like doing this. So my formula for cardiac output, oh, this is it. I don't know what's going on with my my annotations are not wanting to work today. Why? Oh, because I'm on this formula. All right. So let's start with this one. This is a regular cardiac output that we know. Agree? VO2 divided by the AVO2 difference times 10. We got that one. Yes? Okay. So let's take a look at the QS formula, which is a systemic formula. So I put here QS cardiac output so you can understand that better. Yeah, so it makes more sense. So QS cardiac output, systemic flow cardiac output. I want to know how much blood is outside of the body, right? So look at the formula. So I put the formula on the top so you can see it is the same formula here, and same formula here. Yes, they are all exactly the same. Now, on the second case, when we're talking about the systemic formula, because I want to know how much blood is between the aorta and the right atrium. We did talk about that, right? That will be the systemic. So I substituted on the first cardiac output, I'm going to do AO and PA because it is my arterial and my venous samples on a regular cardiac output. So my arterial and my venous sample on the systemic formula is going to be the AO, right? Because the blood leaves the heart oxygenated, and then it comes back to the right atrium. That circle did not work fine for me. There you go. The right atrium. But it is the same formula. I'm just going to substitute in there. Yes? Okay. Let's take a look at the QP formula. Well, locally, it is the same cardiac output. I just added the QP because that will be my pulmonary flow cardiac output. I want to know how much blood is processed in the lungs. Leave the heart to the blood. Leave the heart to the lungs and then comes back to the heart. So I need an arterial sample and a venous sample. So my pulmonary artery is going to have I think I made a mistake here because it's PV minus PA, because the pulmonary vein is going to be my arterial sample and my PA is going to be my venous sample. Yes? And I'll correct this in a minute before I post it on your modules. Like I said, I was just working on it as the 15 minutes that I was waiting here for you. Any questions on the formula? I cannot see you, so
our PV is going to be arterial, and then PA is going to be venous.
So pulmonary vein. Remember that. That's why I gave you the blood flow.
Yeah.
So the pulmonary vein is oxygenated blood, right? So that's the oxygenated blood. Does that make sense? I know it says arterial and venous, PA and PV, right? Arterial and venous, but I want to know the oxygenated blood and the deoxygenated blood in this formula. Because remember, PA and PV, this is the only exemption in which the vessels are the opposite of what we think oxygenated and deoxygenated.
Yes, ma'am.
Okay, perfect. All right, so let me take all this off. And with this, we're going to move on to the first sample that you have on your packet. That will be sample number 3. All right, so we have here, well, before we go that, we saw this on the modules, right? So we already established that for a shunt to exist, there has to be a difference between the pulmonary and the systemic flow, correct? Yes, so the amount of blood that is pumped from the heart to the body should be the same amount of blood from the heart to the lungs. Yes? Yay? Yay or nay?
Yay.
Okay. Thank you. It's kind of hard because I don't see you and I'm not there. So that'll be nice to check this. All right, so so QP, and so make sure remember QP over QS. If I think I have it on the other PowerPoint that I gave you, if QP over QS, which is the ratio, is over, do you guys remember that? It's over 1 or less than 1. But if it's 1, there's no shunt. Everything is beautiful. Yes? All right, so let's go ahead and take a look at the formula here really quickly here. This formula is going to compare the amount of blood pumped into the pulmonary circulation to the amount of blood flow being pumped into the systemic calculation. We compare the saturation of the two systems. The ratio has to be 1 to 1. Okay, so we're going to use the cardiac output formula to resolve for the blood flow. So QS, which is the pulmonary system, is going to be VO2 divided by the AO saturation minus the mixed venous saturation times 10. Why do I have the mixed venous saturation here? Because I truly want to know. So imagine if there's a shunt in the atria. right? So there's a mix of blood, oxygenated, deoxygenated. So if I go ahead and take a sample of the right atrium, what would, and if I have a shunt, that will not be a true value. So what I really want to know is when right before the blood comes into the heart, that will be SVC and IVC, right? So the doctors, if they are doing a true shunt study, they're gonna that's one is if it's gonna come from oral, it's gonna stop at the IVC, take a sample, and then pass and go above to get a sample from SVC, and then get the hemoglobin and the oxygenation. Yes. So for QS, I will have to resolve for mix if I have that information. If I have SBC and IBC, I'm going to get that information and get mixed through the Flam's equation. Do we remember the Flam's equation? 3 SBCs plus 1 IBC divided by 4. Okay. If I have the information, chicken parm, remember. Okay. If I don't have SBC and IBC, what else can I do? Where does my SBC and IBC mix?
The RA.
In the RA, perfect. So if I don't have SVC and IVC, I should not use the Flam's equation because I don't have it. And then I'm going to use RA if that's the case. But if I do have SVC and IVC, then I'm going to use mixed venous through the Flam's equation. Yes? Okay. On my QP, let me see, maybe I can get a circle instead. That would be probably best. On QP, I'm going to use PV minus PA. My oxygenated blood minus my deoxygenated blood saturation. And it is the cardiac output formula, VO2, and this is A, right? This is arterial, or this is the oxygenated blood and the oxygenated blood, just like it is in cardiac output.
So, sorry, I have a question. Is that the AO stat? Because on one of the number 3, when it asks us for, it says SaO2 use AO. So would that be the TO2?
Let's get to that formula here in a moment. So
Okay.
you're onto something, but let's do one step at a time. So remind me when we get to the formula, okay? So we are just revising the formulas so they match in our brain. That is just cardiac output. It's just like a small system. Yeah, it's a systemic or the pulmonary system instead of a general cardiac output. Yes. So I just wanted to put it like this so you can see what the each one is. Okay. So and then we have the concepts here, right? So for AaO2 is the systemic arterial oxygen, which is going to be the first one coming out of the heart, right? That's the AO. Then my venous, again, if you do have SVC and IVC, this is what mixed venous saturation is. So sometimes the confusion is, what pieces do I use for QS and QP? QS is the system, is the body. So I need the blood outside of the body. So the blood outside of the body goes through the AO and comes back to SVC and IVC, correct? Though that blood does not get to the lungs, just outside of the heart. Both systems are outside of the heart, one to the body, one to the lungs. Therefore, when I'm looking for my pulmonary flow, I'm just going to see what goes to the lungs and what comes back from the lungs. So that's how am I going to plug this information here for QP. Pulmonary venous, because it goes to the heart, and then pulmonary artery, I'm sorry, pulmonary vein is going to carry blood to the heart, which is already oxygenated, and then the pulmonary artery goes out to the lungs, deoxygenated. Yeah, so it is the same cardiac output formula. Very same. So it's just chicken parm. What am I going to need here? All right. With that being said, let's start working on, this is your practice number 3. Yes, on your packet. Okay, I'm gonna pull here my information. Again, remember that this problem is on the board in the classroom, so you can see it better or have it like handy for you. Okay, so the first thing, when I get patient information, right, I'm gonna see this, and I'm gonna take a look and see if I have all the ingredients for a chicken parm. I'm gonna take a look at what is this problem asking, right? So it's asking for BSA. What is my cursor here? It's asking for BSA. Do I have the elements to get BSA? Hypothetically, what information do I need for BSA?
Height and weight.
Height and weight, do I have it?
Yes.
I do, perfect. All right, the next one is VO2. What elements do I need for VO2?
Let's say and constant 125.
BSA, right? So if I resolve for BSA, then I'm golden there. All right, so the next one is, look at number 4, fake cardiac output. Therefore, this ABDO2 difference is just for cardiac output, regular cardiac output. I just want to establish what is going on first with the patient because I'm investigating, right? So for ABDO2, what information do I need? Which is the bottom of my formula for cardiac output, right? Do I have information to get VD difference?
O2 consumption, yes.
I
Yes.
have, uh,
Yeah.
okay. Oh, yes. And because I'm gonna work with my, on my diagrams with diagram A, correct?
Okay.
Okay, so on diagram A, do I have, it says here, use AO. Do I have AO on my diagram? Saturation? I do, right? And then, oh my goodness, that's Houston calling, like why? And then PA, do I have PA on my diagram?
Yes.
Okay, so I can resolve for AVDO2, right? So I have BSA, I have the VO2, and AVDO2. Now, can I get FIC with this information? Totally, right? Because that's my formula, VO2 by AVDO2 times 10. So yes, I do have. So I want you to work in a process like that, right? One thing at a time. Don't get too nervous. Go with the flow, right? Trust that you know what you're doing. If it asking VSA, VO2, ABDO2, okay, that's FIC. Okay. Do I have a number for FIC? Okay, perfect. Now I'm going to investigate the shunt. This is where I'm going to start looking for the chicken farm situation. Okay. Let me get my, what do I get here? Okay, I'm gonna get an arrow. All right, no, not an arrow. I want, hang on. Oh, I want a pencil. Pen, okay. Now I have CO2, CVO2, and look at this, PA and PV. On your numbers here, number 8, it says CCO2. It should be PVO2 on number 8 on your formulas, on your packet. Okay, so we're gonna use this too. And we're going to use this too. With this one on the top, I'm going to do QS. And the one on the bottom, obviously, because it's the pulmonary, right? I'm going to do it for QP. And then with this two, with QS and QP, can I get shunt? Yes. So the first 4 is to determine the general cardiac output on my patient. Nothing else, right? But the general cardiac output of my patient doesn't tell me if there's a shunt. It only tells me how much blood is through the body, period. Because on cardiac output, I'm going to get AO and PA. So it involves the 2 systems. Okay. Now I need to investigate the entire system and then the 2 subsystems per se. Okay. All right. So the first thing I think I'm going to change to text. All right. So let's go ahead and resolve for BSA. So using the Moseller's formula, because I already did this. So this is going to be 2.08 square meters. On your exam, I'm going to give you BSAs. So you don't have to worry about getting BSA, but on your RCIS, you might be asked, which formulas do we use for BSA? The most common is going to be Mosaller. Okay. So let's resolve for, I'm going to start here to resolve for VO2. So what is the formula for VO2?
25 times 2,
Um,
25 times
so it's
4.
going to be BSA times 125 because that's the constant, right? So if I substitute these values, and I like to work like this because if I miss, I can go back and locate where I miss instead of not finding it ever, right? So BSA is 2.08 times 125, which I believe is like 260 or something like that,
260.
right?
Yes.
So it's going to be 260. Do not give me what is it called? Don't give me units on this one, right? Even though it's oxygenation, right? I'm sorry, it's not oxygenation, it's the assumed oxygen, right? Okay, I already resolved for two. So I'm gonna do here 260. All right, and then on my next one, I'm going to resolve for A, B, oh my goodness. It's kind of hard not to work on the board, ABDO2. So what is the formula for ABDO2?
SbO2 minus S or SaO2 minus Sb.
Okay, perfect. I like that. So SaO2 is actually lowercase, right? O2 minus SV O2. All right, do I have that information? Or to resolve, right? Oh, this is going to be, sorry, this is going to be the difference, right? It has to be difference because when it says difference, I'm going to have to use my constants and everything. So now I have to dissect this formula. So it's going to be I minus V difference O2. Okay, I'm going to go ahead and I can go ahead and substitute the whole entire formula at once, or I can do it one at a time. Okay, so, okay, if I'm going to work on arterial, what side do I get?
91%.
91%, right? Looking at my formula here. So I have 0.91 because it's percentage times, what is my constant?
1.36.
1.36. And what else do I need for this formula?
The venous.
Hemoglobin.
Before this, I'm getting the saturation, right? Because 0.91 is the oxygenation, but I need to know the saturation. So for that, don't I need hemoglobin? Because see, the hemoglobin tells me how good the cells, the red blood cells are carrying oxygen, right? So the ability of the cell to carry oxygen is my constant. And then I need to know what is my hemoglobin. So don't forget your hemoglobin on your formula. If you forget your formula, your hemoglobin, that's going to throw off the entire thing. Yeah. And then minus, and I'm going to go ahead and work for, so what is my venous that I can use here?
76.7.
76.76 times what?
1.36.
And times my hemoglobin, right? I'm going to open my thing here a little bit more. Oh, no. Okay, well, I'm going to have to open another square here because it moved. Let's see if I do a good job aligning the universe here. All right, so let's go ahead and resolve AB. And again, I know it's like, oh my gosh, do I have to write it down every single time? My answer will be yes, because that's going to make it a lot easier. So now I'm getting my calculator because again, I thought I was going to see you on the in classroom, but I forgot Mr. Cho is going. So it's going to be 0.91 times 1.36 times 15. So this is 18.56. minus, and I'm gonna do my other calculation, which is 0.76 times 1.36 times 15, which is my hemoglobin. So it's 15.5. Everybody with me? Are you doing it on your papers? Do you have a calculator available?
Yes.
Yes, okay. So is that a good number?
Yes.
Yes, okay. So I'm gonna use 2 decimals as we have spoke, minus 15.5. So my result here is 3.06.
Okay.
Right? So I'm gonna come back here. So it's 3.06. All right. And then my number 4, I'm gonna get fake cardiac output, which is the gold standard, by the way, right? So cardiac output is equal VO2 divided by.
AV difference.
Mhm. And I just got this, right?
Mhm.
AV difference times 10. All I have to do, because I already have all the solutions from before, is going to be 260 divided by 3.06 times 10. I'm going to go one more step and resolve for my dividend over there. Maybe 260 divided by 30.6. Okay. Does anybody have cardiac output?
8.49.
8.49. Everybody agree on that?
Yes.
Okay, what are the units?
Liters per minute.
Liters per minute. This is telling me how much blood is circulating or ejected from the heart to the system entirely, right? So cardiac output. Okay, so I'm going to come back here and I'm going to do cardiac output is 8.49 liters per minute. I'm already having some clues here because we know that what is their normal cardiac output value?
Is it 4 to 7?
Mm-hmm. 4 to 6. I've never seen anything like that. Oh, that tall guy that I had at 6 something. I've never seen any higher than that. And I've seen very, very low, 2 point whatever, which is, you can imagine. Okay. So now I have a basic idea of what is happening to my patient, right? Like, okay, well, let's take a look at individually in the systems. All right. So I'm going to resolve. Where's my cursor here? I'm going to go ahead and resolve. Oh, this is a cursor. I'm going to go ahead and resolve for QS, and then QV elements first. Okay. So the first thing that I'm going to do, I have a question. Yes. Okay. The first thing that I'm going to do is I'm going to resolve for, how about QS? Yes. So according to my formula, QS is VO2
Divided by AO saturation.
Okay, so divided by AO minus mixed venous oxygen saturation. Oh my goodness, because I'm working on capital letters, so it's kind of like back and forth, right? And then times 10. Everybody agrees? All right. Okay, so let's go ahead and maybe I can do all caps and then whatever, whenever I have to go down. Okay, QS equals. Do I have VO2?
Mhm.
I already pulled VO2, so I'm gonna go ahead and plug it at once. All right, now you have to remember, oh, this one, I forgot to say difference. Or SAT, right? SAT. And this is SAT. Because saturation is different than oxygenation, right? Saturation difference. That will be the actual formula. All right, so I'm going to go ahead and start substituting the values, just like I did for cardiac output on the top, right? So for my system, which two pieces of information do I need? I need AO and I need mixed Venus. So I can go ahead and start. I know I already use AO, which is 0.91 times what? I'm using cardiac output.
76. Oh.
No.
Oh, 1.3536.
Oh, now we know. So it is a cardiac output. When it says saturation, it's not the same as oxygenation. When we see 91, that's the oxygen. That's not saturation. Yes. So if it says saturation, you have to multiply by the constant by hemoglobin. So hemoglobin here will be 15. Now in real life, when we get samples from hemoglobin, it's going to be all over the place, right? We never get the same number. So it's going to be this minus. All right, let's take a look at our graphic A. Can I get mix venous saturation?
It's 71. PA.
So I'm not using PA, I'm working on the system. There's no PA on the system. The system is the body. So what is the mixed venous saturation?
Is it the IVC and SVC?
Uh-huh, correct. And then go to your graphic on A. Do I have SVC or SVC or IVC? Do you see SVC or IVC on graphic A? Don't be scared. Say no, because there's none.
Yeah, I don't.
So why are you scared to say no?
I'm not. I'm looking.
Okay, so it is not. So when you take the test, I want you to know what ingredients do you need for your chicken parm. In this case, I do not have breading. I do not have SBC and IBC. So what can I do to substitute this breading for my chicken parm? I'm going to go ahead and use what? Say it.
The RAs.
Yes. I'm going to use the RA because that's where the blood mixes. Remember, in absence of some information, I can substitute just like your recipe. You just have to make sure that it equals, right? In reality, in the right atrium, the blood from the SVC and IVC mixes. Okay. All right. So if I have already determined that there's no SVC and IVC, I'm going to use RA. So what is my saturation for RA?
78.
Okay, 78. Oh, I forgot my, so 78, and then what?
It's 1.
Times, times
15 hemoglobin.
15. I always have to use my hemoglobin. I guess I'm gonna make this one a little longer. I lost it again. I don't know why it doesn't let you kind of continue there. All right, maybe a little out. All right, so let's go ahead and, oh, and then on this sample here, the only thing will be times 10. Right? Okay, so can I go ahead and resolve for that? That's gonna be like super easy to resolve, right? So go ahead and resolve on your own while I work on this. Well, I already have the one from the top, which is 18.56 is the same. Minus
15.91.
15?
0.91.
15.91. Everybody got that?
Yeah.
Yeah, perfect. All right. And then I can go ahead. So when you do it methodically like this, I know it's tedious, but it allows you, it gives you the opportunity to come back and find if you made a mistake. Okay, so I have 18.56. Remember, 2 decimals minus 15.91, 2.65. And 10, and then I'm going to do the thing again. Q is equals 206 divided by 26.5.
The VO2, I think, is 260.
Oh, thank you. Well, dyslexic today, I guess. Thank you, Grace. 60 and 60 0. Okay, so I'm going to do 260 divided by 2.65. Oh, 26.5. So my QS, which is my systemic cardiac output, is 9.81. And what are the units? I'm gonna let you answer this because I've said it like 5 times, 6 times, 7 times. We are working with which formula?
Cardiac output.
Cardiac output. So what are the units for cardiac output?
Liters per minute.
Liters per minute. So right now, I'm investigating what is the mini cardiac output from the system. And the next one, I'm going to do the mini cardiac output. And I'm going to say mini just because it's a sub. It's not mini at all. I'm going to get the cardiac output for the pulmonary system. Cardiac output for the system, cardiac output for the pulmonary system. Yes?
Yes.
Or pulmonary flow. Let's put it that way so we don't use the same words. All right. So actually here, I think we stepped a little, we went ahead. So on here, my answer is going to be 18.56. Here is going to be 15.91. Yes? Okay. And then, so I've already resolved for my QS, systemic, AO to RA. All right. If I work here in the bottom, can you still see, or do I work on the top? Well, let's work on the bottom so we can have the other formula here. Everybody can see? I will assume. All right, now let's work on QP. So my formula for QP is VO2. I'm telling you, I'm dyslexic today. Why did I use S instead of a 2? All right, VO2 divided by what now? Because I'm working on my pulmonary system.
PA saturation and pulmonary artery and pulmonary vein.
Well, yeah, so pulmonary, so I need the arterial first, arterial in the sense of oxygenated blood, right? So I'm going to use PV. So I'm going to use PVO2 sat minus PaO2 sat, and all that multiplied by 10. Let me use a parenthesis because sometimes if we forget something, that is miss. Right? If you look at this one and this one on the top, they look exactly the same. It's just different pieces of oxygenated blood and deoxygenated blood, depending on where I'm looking at. If it says pulmonary, I'm going to use pulmonary vein and pulmonary artery. Okay, pulmonary vein is coming to the heart oxygenated. So I'm going to use the oxygenated first. So if it makes more sense, I'm going to use the higher oxygen minus the lower oxygen, if that makes sense on this particular one. All right, so let's keep working on this one. QP equals, I already have 260 before I mess it around again. Now, what is my PV saturation here? I'm going to go ahead and plug everything. Here's my PV. Go look at your diagram. Look at A. What is my oxygen for PV?
7.76.
On your diagram? Diagram A. I need oxygen for PB.
78%, right? So atrium
Why did you use atrium?
on the right side, because it's
Because I'm looking for PV.
Would-
So that is the right answer, but I want to know why you use LA.
vein is venous and A is arterial and
Yeah,
venous is
yeah. But what is your pulmonary vein saturation on diagram A? Can you guys look on the diagram and identify the pulmonary veins?
it just shows the pulmonary
It
artery.
gives us the PA sat though, right?
I'm looking for PV,
Was it 78?
which is pulmonary vein. The pulmonary vein comes or it goes to the heart? Comes to the heart or it goes away to the heart? The pulmonary
I
vein?
mean, well, on the diagram, it's only giving the PA sat. I don't know why
Okay,
you're
so
getting the P.
all right, chicken parm then. If I don't have it, what can I do? Where does the pulmonary vein drops? It's
In the
blood.
LA.
In the what?
The left
Left atrium.
Left atrium, right? Just like the same thing that we did for the pulmonary for the SVC and IVC, correct? Now, if you on your image on this final test, on your RCIS, if you don't have the information, look for the substitute that is going to give me, the same result. All right, so the reason I'm using the LA is because the pulmonary vein, I don't have the saturation or the oxygenation. And then I go to the next chamber, which is exactly the same value. Now, if the shunt is on the atrium on the sample, it will be a mess because I don't have SVC, IVC, and I don't have pulmonary vein. I'm using substitutes. So it's not a true number, but it's the best thing I can do. Okay, so what is my PV then? What is my PV oxygen?
0.98.
498, and then? How do I get saturation?
76 times 1.
Yes, times 1.36 times. So don't do it straight. 0.98 minus 70, yada yada, right? We have to develop the desaturation formula times what else?
Hemoglobin.
Hemoglobin. Perfect. I'm gonna close the parentheses. Then I'm gonna do minus, and then I'm gonna go now to my PA. What is my PA now?
76.
0.76. Times
1.36.
mhm,
15.
times 15 because that's my hemoglobin. And then all that times 10. Okay, so I'm gonna go ahead and just substitute the values. QP equals to 60. .98 times 1.36 times 15, that is 1999. Let me use my thing. Minus 0.78 times 1.36 times 15, that one is 15.91. And I'm gonna close my parentheses and then times 10. So I'm gonna resolve for QP here to 60 divided 1999 minus 15.91 equals 4.08 times 10 QP. I know it seems like forever, but it's going to be 40.8. And then my last result going to be 260 divided by 40.8. So here my QP is going to be equals 6.37. And what are my units?
Liters per minute.
Liters per minute. I'm only working on cardiac output. Look at the formula. All three are going to be liters per minute. So I just want to know, look at the concept. How much blood is pumped to the system, or how much blood is pumped to the pulmonary system every minute. So the fact that it says minute, okay, liters per minute. I cannot work on CCs because that's stroke volume. I don't want to know one stroke. I want to know the whole minute. Okay. So now I do have, okay, so let me resolve for this here. It's going to be 1999. And this one is going to be 15.91. Good. All right. Now the next question is, go ahead.
So you know how for number 6, the CVO2, how you plugged in the 15.9.
Mm-hmm.
So we're not using because whenever I was doing it, I plugged in the answer for the very first AV difference that we did.
Mm-hmm.
So that I plugged in 15.50. Do you not want us
It
to
could be,
use
it could be,
that?
no. I think it's 5.5 because on the second one,
Uh-huh.
on this
On
one,
the
hold on. Let me just annotate so you can tell me where is this that you're asking. On this one?
no, like if you go further up when we did the very first AV difference,
Uh-huh. This?
of the 15.5, yeah.
Uh-huh.
So
Mm-hmm.
as I'm going through the steps, like after we get the AV difference and then we go to FIC, so that the CaO2 and the CvO2, those were the two values that I'm using, like the 18.56 and the 15.5.
15.6.
Or is that not?
15.6 and 15.5?
Yeah. And then on
Where's the
but
15.6?
down no, 18.56.
Oh, uh-huh.
And the and then the 15.5.
Mm-hmm.
So those were the two values that I plugged in for number 5 and 6 on the side where it says
Yeah.
software.
But no. Because I'm gonna tell you why.
No?
Because
Okay.
because on cardiac output, this value. So let me use a annotate here. Maybe a circle. Here for what is the unit? Maybe an arrow. What is the unit that you use for here? What saturation? What oxygen do I use? AO
That
and
one
what
was
else?
for the
AO
AO
and
the PA.
PA, right? So here, what do I use? AO and
AO and the RA.
RA. And here, what do I use here?
Pulmonary vein.
PV and PA,
Uh-huh.
right? So you cannot use for the bottom ones for 5 and 6. You cannot use it entirely. I mean, you use the same, you use AO here, but this one here is RA. This one here is RA, is not PA. Because there's a difference. That's 0.78 and 0.76. Now you can use it for cardiac output, but you cannot use it for QS. Because in the system, we are not using anything inside of the heart. We're using outside of the heart. And unless we don't have SVC and IVC, then we use RA, but we cannot use PA for system. I mean, it's going to be very close, right? The numbers are very close because it's 0.78 and 0.76. So it looks like it could be used for the same thing. Oh, no. Does that make sense or no?
Yeah, that makes sense.
I had a question. I don't know if this is what she was trying to say, but for the last equation we did when you did the 0.76 times 1.36 times 15, I keep getting 15.5 and not the 15.
Oh, okay. So let me see. Did I get that number? Okay, so it's 0.76 times 1.36 times 15. Okay, 15.5. Ah,
What are we doing?
15.5 here on this one. So maybe I did 0.78 instead of 0.76.
Oh,
So
yeah.
here, because I cannot correct it, go back and correct it.
7, 8.
15.5, 1999. So it's going to be 1999 minus 15.5, right?
It's 15.9.
Yeah, that's what
Okay. So it's 4.49.
yes.
Okay, so let me erase. Oh. No, it's not gonna let me. It's not gonna let me scratch. So it's going to be four. What did I say? 1999 minus 15.5 equals 449.
Mm-hmm.
So it's 44.9. 260 divided by 44.9.
Yeah, so I got
44.9.
5.7.
Okay, 5.79. That makes more sense.
Oh, I'm
So
confused.
let's do it again. Let's do it again. I just missed here on this result right here. Let me get a circle. Ah, I think it's this. I don't know where my circles went here. I made a mistake on this one because I think instead of doing 0.76, I did 0.78. So when we resolve for 0.76, it is 15.50. So let me go ahead and resolve this again. That might make much more sense. Now it doesn't want to go. Okay.
So the 0.98 is
So scratch this and scratch the rest. Scratch this, and scratch this. Okay. So let me do the formula again here. Text. All right. So QP. We're looking at the pulmonary system. So I only need PA and PV for oxygen. So it's going to be VO2 divided by parentheses PV O2 sat minus PA O2 sat difference, right? Times 10. So that's my formula again. I'm just going to substitute the first the number that I missed. So QP is going to be equals 260, and then I'm going to substitute the values here. So the values that I'm going to use is 0.98, 0.98 because that is my most oxygenated blood times 1.36 times 15 minus, another parenthesis, 0.76 times 1.36 times 15, which is my hemoglobin, parentheses, and all this times 10. Don't let it go. There you go. So when I resolve for this, QP is going to be equals 260 divided by parentheses 1990 minus 1550 times 10. QP equals 260 divided, so it's 579, right? Oh, no, that's a total. So 1990 minus 15.5, 1999, correct? 1999 here.
15.50 or 15.5?
It is 15, I thought it was 15.5, isn't it? Let me do it again. 0.76 times 1.36 times 15, 15.5. So this 1999 minus 15.5 equals 449. 4.49. times 10. QP equals 260 divided by 44.9. And QP equals 260 divided by 44.9, 5.79 liters per minute. Okay. So I made the mistake here on 0.76. I think I saw 0.76 and maybe I went on my calculator to go 7. So on your exam, say you made the mistake that I made, right? You put a different number. So I want you to see, that's why I want you to see, I'm going to pick up the papers because I want to see you did these formulas. So if you did the right formula, you're still going to get credit. You might not have the right answer, but you have credit for everything else. All right, so I resolved for QP and also this, therefore, this one, I don't know if I can remove it though. Let's see if we can remove it. Oh, we can. All right, so then here, PbO2 was 50, and I have it right, 55. So what is the shunt now? So my formula says, you guys have your currents book. So your shunts are on chapter 4. Oh no, yeah, this is chapter 4. Well, I think I have a different book, but you can find your shunts on. Mine is on chapter 4. Okay, so on my to investigate which way is my shunt. Now I need to know. My formula is going to be QP over QS. So it's QP over QS. So I'm going to substitute. So QP is 5.76, correct? Over 9.81. Because I want to get the ratio. So go ahead and divide. So it's 5.76 divided 9.81. So it's 0.58. Is that correct?
The shunt formula.
So do I have 5.58? Everybody got that? Yes? Yes, no, yes, no?
For the QP, I got 5.79. So
That's fine.
but it only changes it.
That's fine.
So I got 0.59.
Okay, that's fine.
That's what I got also.
Okay, fine, because you probably use another decimal, which is fine.
So, how are we getting that 5.76 and 9.81?
This is the QP and the QR results that we just got. So this is a QP and this is a QS.
Oh, okay. Okay.
So I'm going to substitute here and my result is 0.58. So we said when your value is less than 1, when your value, let me write it down here. It is on your PowerPoints anyways. If your ratio, oh, I guess now I can remove, right? Ratio is less than 1. So your shunt is going to be right to left. If your ratio is bigger than 1, your shunt is going to be left to right. So in this case, what's a ratio?
Left to right.
Right? So the ratio is 0.58. Is that more or less than 1?
Less than 1.
Less than 1. So if I go down to my next information here, it says if it's less than 1, my shunt is going to be right to left. So what is happening here, and you can tell here by the difference in the two, right? So I have more blood in the system than I have in the lungs. So that means the right side, the lungs are giving more blood to the system than one is receiving. The system, the shunt, the blood in the right side of the heart is pushing to the left side of the heart before it leaves. That's why there is a difference. So if the blood that goes to the system is 9.8, and the blood that goes to the lungs, which is what is processed in the lungs, is 5.76, that means, so if I have a heart, let me draw a heart here. That might be a better one, right? So this is my heart, and this is my septum, right? And I have my RA, LA, RV, and then the LV, right? So there is a problem in the shunt, right? There's a problem in the shunts, correct? Now, if the blood goes, maybe I can get an arrow here. That will work. And how about the different color? Here and with the different color. So the blood that comes here, right, gets to the RA, and it should be processed here, and it should be sent out to the lungs, right? So the blood that is processed in the lungs is 5.76. And then the blood that goes out to the system through the ventricle is 9.8. So how is this side getting more? From where? So the blood goes that way. So there's a shunt, either in the right atrium or the right ventricle. Now let's go ahead and take a look at your graphic A on your samples. When you look at the difference on the saturations here, what is the normal saturation for the RA? When it comes back to the heart, it's about 75, correct? So look at your chambers here. Is 78 closer to 75? I need a yay or nay.
Yes.
Yes, okay. How about, so if the blood follows and there's no shunt, or there's no problems, my next chamber should be okay, which the RV, is that okay or no? Yeah, right? Because from the right atrium goes to the right ventricle. So if everything is okay, we should be okay, right? If there was a shunt in the right atrium, what would my oxygen be on the right atrium if there was a shunt from the left side to the right side? So if oxygen is coming to the right side, it will increase, right? So I will see a difference right away. So out of your 4 chambers, where do you see a problem? Look at your oxygenation here. Out of the 4 chambers, where is the problem?
I think it's in the left ventricle
Why?
because it's so low. Normally it's like 95%. It should be higher since it came from the lungs.
Perfect. Perfect. So I should know what normal is to know what is abnormal. Now, just the fact that the left atrium has 98, that's the blood coming right from the lungs, right? Coming down to the left ventricle, it should be 98 as well. Maybe loses 1 point in the travel, but not more than that. So the fact that it says 92, that is telling me, so how can an average goes down? How can 92 go down from 98?
There's blood coming from the
Because the 78% is going through the ventricle from the right to the left ventricle, is contaminating the right side. And when we bring lower oxygen to a higher oxygen, is going to reduce the oxygen. Does that make sense?
Yes.
Perfect. All right. Now, let's take a look at sample B, just to take a sample, just to take a look. Look at your chambers. Where is the problem?
The problem is on the right side in the RA and in the RV.
So
Oh.
there can only be one problem. So
only
pick.
one?
Mm-hmm. One chamber is a problem.
Right ventricle.
Why?
Because it's the blood that pumps, that goes to the lungs to get oxygenated.
No, that doesn't matter. So looking at those four chambers, are those normal stats?
No. The right side is increased.
The right side is increased, right? So where is the problem? Which chamber is a problem? Hmm?
Atrium.
So is it atrium or is atrium? So you're saying or you're questioning?
If it's increased, doesn't that mean blood from the left side's going to the right side?
Yes. So if I have a septal defect on the atria and it's a shunt, so this will be a right to left or left to right shunt on sample B?
That one would be left to right.
Left to right, right? So I already determined it's going to be in the atria and it's going to be a left shunt, right? So the left atria is shunting oxygenated blood, oxygen-rich blood to the deoxygenated blood, right? So that's why the atria now increases the oxygenation because it's receiving like 98% blood into its probably 75. Yes?
So how would you know that it's for the atria and not for the ventricle on the right side? Since it's
Because
the
how do
same
you
percent?
explain 82 on the atria if it was in the ventricle? If you were to have a ventricular septal defect left to right, your right atrium will be normal.
Oh, okay.
So it'll be
Because
75,
of the way
82.
that it flows. That makes
Mhm.
sense.
Yeah, there's no way the 82 from the ventricle goes up to the atria on the right side,
Yeah, it doesn't go backwards.
right? That's why we have the valves, correct?
That's good. Yeah.
All right, so
Thank you for explaining. That makes
yeah,
sense
yeah.
now.
So, everything, so you have to look at where the problem starts,
Okay.
but you need to know what normal is to know what abnormal is to recognize, right? Now, with this in mind, when you go do your calculations, it has to match, right? All these things that we're doing here. Yeah? Any questions?
I have one question.
Mhm.
I know for the shunt, the formula QP divided by QS, that 5.76, I actually got 5.79.
That's fine.
Okay.
Does it make a difference on the right or left shunt? No, right? So that's what I'm saying. So you have to determine if the point is critical, the 0.9 or 0.6. If it was 0.998, I will almost say there's no shunt, right? Because the difference, or 0.99998 or something like that, right? That will be very equal to 1. So there's no shunt. There might be a little tiny hole, but at this rate, it's actually okay. So that's how you are going to resolve number 4 and number 5. So just make the correction for number 8 is PVO2 on your samples because it says CC. Now, did you see that on this particular sample, we have all kind of information that we don't need? Like, for example, let me get this out of the way. Like this, for example.
Yeah, I don't even know what that is.
then if you don't even know what it is, then you don't use it, right? It's not for you to use. So on your RCIS, it's going to be like this. You're going to have a lot of information that you don't need, is to trick. So I want you to know you can do what you know, right? So height and weight. Obviously, I don't know if you're going to be asked to actually convert or anything, but that will be good that you practice converting height and weight into metric system, because you may or may not. I am not sure. The test just changed. In general, it is the same concepts, but the questions that are related to each topic might be a little bit different. So I don't know. They might ask you, how do you convert height into metric? And then you already know you multiply by 2.54, right? Or your weight, you divide by 2.2. Okay. Do we have any questions? No? You guys think you can do 4 and 5?
I think
Because they're
so.
exactly the same. They're exactly the same.
Oh,
Yeah, I think honestly, like now knowing, because when I was looking at it, I'm like, well, how the heck do we get PV? Like we don't have PV, right?
Well, it wasn't even
Now
looking
knowing like okay,
animations on there.
substitute that,
Mhm.
and like the mixed Venus, now I know I can substitute that. So I'm like, okay, it makes sense. That's all I need
Chicken
to know.
parm. We'll be talking about chicken parm. Even when remember we talked about on your exam that you have to see what you have. Oh, I erased it again. Oops, I did again. What do you have, right? The first thing that you're gonna have to look in, what are my questions? What is this question about? Right? Look at this. So you solve for what? All right. Then when you look at this, then you're gonna go up and down. Can I do BSA? Yes. Can I do VO2? Yes, because I have BSA. Can I do everyday? I have the graph. Yes. Can I get fake with this? Yes, yes, yes. And then you have all the information, right? That's how you can dismiss what is not useful. And the other two are exactly the same. Exactly the same. Any other question? No? No, no, no. Okay. So the other two should be as simple, very simple, just like those two. I mean, like this, resolving for BSA, VO2, one step at a time, get focused on what you know. All right, guys. Well, we'll see you guys on, well, not this Monday, but the following one. Well, I'll see you next week for clinicals. Yeah?
can I ask you a quick question?
Yeah.
On Canvas for the assignment for providing grounds, that now counts to our grade?
No, it has never counted your grade, but it has to be 80% to obtain 04.
Oh, okay. Okay.
Yeah, but if you're not participating on this, it is not great. It's not great for you.
Yeah, I guess there was some confusion in the group chat about whether we have to do it or not and if it's graded.
No, we talk about it. It's completely volunteer.
Okay.
So you can go ahead and resolve, right? Use this information to actually resolve for the shunt that you have if you're doing the critical thinking batch.
Okay.
All right. Bueno, if there's no more questions, I'm gonna let you guys go, and I'll see you shortly or next week. Yeah.
Okay.
Bueno.
Okay, thank you.
Adios. You're welcome.
Bye.
Bye-bye.
Thank you.